All right, thank you everyone for attending or watching this second lecture in the Automotive Engineering Fundamentals course. So in this lecture, we're going to look at internal combustion engine, that's ICE, ICE. We're not actually going to look at frozen water. Whenever we see ICE in this course, we mean internal combustion engine. So we're going to look at the main components. A lot of this is going to be a terminology, labeling diagrams, and stuff of that nature, make sure we're all on the same page when we name different components and talk about different terminologies. And then we're going to briefly look at the operation of internal combustion engines. So with last class, we had the instructor and GA information. Some of this was still to be determined. We talked about the mark breakdown and my expectations for the course and how those expectations are somewhat modified because of the COVID-19 situation. And then we also talked about automotive engineering history. Now in this class, what are we going to cover? Well, the first question we're going to be is, why are we studying internal combustion engines? That's a question that has to be answered. We're then going to talk about the definition of an internal combustion engine, what an internal combustion engine is and what it's not. There's going to be a number of slides that look at the basic components of internal combustion engine and give definitions. There's going to be subsequent slides about terminology. Now for these slides in this lecture, I'm not going to read the terminology or the definitions verbatim, because that's what I would be doing. So instead, I'll simply pause for a few seconds on each of those slides, and the expectation is that you as a student will pause the playback of this video and read the definitions and look at the terminology and pace it as you need. So after that, and that's actually the bulk of the lecture, is the components and the terminology. I'm then going to talk a bit about spark ignition versus compression ignition engine operation. Then I'm going to talk about four-stroke in the context of SI and CI engines as well. And then I'm going to very, very briefly talk about two-stroke engines. And as I said, this course is going to give you an introduction to internal combustion engines. You will take a course in fourth year that is more specialized, and the entire course focuses on internal combustion engine design. Okay, so normally I would do a think, pair, share at this point in the course, but again, given where we are with COVID-19, I'm going to skip over this think, pair, share because there really is an answer that I kind of want to bring everybody towards. And really the idea is because they are not dead. Contrary to news reports you'll see saying this is the death of the internal combustion engine, et cetera, they're not dead yet, and they're actually still going to be alive after I'm dead, actually. Although anyone who says the internal combustion engine is not shrinking in terms of its relevance in the automotive industry is also fooling themselves. So they are dying, and that's a fact. So this graph here is a prediction of new car sales globally up until about 2040. So the total number of car sales is expected to rise from about 80 million in 2015 to about 120 million in 2040. So it's an increase, but not crazy. Now, currently of the 80 million cars, essentially 80 million of them use some form of internal combustion engine. So they're either pure internal combustion engine or hybrid cars. And by 2040, though, this isn't actually changing a whole heck of a lot. The share of pure electric vehicles will only be 35%. So by 2040, what this is saying, pure electrics will still only be 35% of the market share. Well, that means the other 65%, or 52 million cars being sold, will still use internal combustion engines in some form. And actually the total amount is actually going up, because since the total number of sales is going up, we're actually going to be selling more vehicles with internal combustion engines. So yes, internal combustion engine sales will begin to decline, but not at the rate that is stated by media governments. There is no way that British Columbia will be all zero emission vehicles by 2040. Simply the infrastructure is not there from an electrical grid capacity to be able to charge if everyone drove an electric vehicle in BC, there is not enough capacity in the electrical grid to be able to accomplish that. And in order to accomplish that, they would have to be building a new nuclear power plant about I think it was every 5 years until 2040, or maybe it was every year. It was something at very, very fast pace. So in other words, it's pure political, whatever you want to call it. Now, when you talk about it now, I don't disagree, though, that by sometime in the future, maybe 2060, 2070, yes, the internal combustion engine will finally be put to bed, maybe 2080. And the main obstacles that are really kind of stopping electric vehicles from taking over the market at a much more rapid rate is the infrastructure. You have to replace all the gas stations with charging stations. This costs billions of dollars. Driving ranges are an issue. Cold weather is an issue. This is really very important for Canada. We tend to live far from work, and we tend to have this nice weather called winter. Long road trips tend to be very common in Canada because, well, unlike Europe, our railway system sucks. And we have nasty winters. So EVs are likely to take longer to take hold in Canada than the rest of the world. And then the question is, as I stated before, even if EVs take over, how is the electricity going to be generated? Right, and as I said, right now, if everyone started driving an EV, the power grid would be overwhelmed, and we would be forced to burn coal to make up the gap because we don't have enough renewable energy sources. Well, burning coal is actually a lot worse for the environment than burning gasoline or burning diesel. What's actually happening in China, China is very pro-electric vehicle. Well, China gets most of their electrical energy from coal, and so does the States. So essentially, we have coal-powered vehicles driving around. Well, that's terrible for the environment and terrible for human health. Now, there is a benefit, though, in that the pollution is being transferred from maybe the city center, where you have a bunch of vehicles, to somewhere out in the country where the coal plant is present. So there are benefits, but it's definitely not, the joke right now is that everyone in California with an electric vehicle is driving a coal-powered vehicle. We're not there in terms of having the renewable energy resources to be able to have a net zero emission of carbon from vehicles. So yes, they are not dead. They're going to be around for a long time, probably before anyone in this class has also passed away. Definitely after I've passed away, but you still have to recognize the fact that their market share is shrinking. Okay, so now that we've gotten that out of the way, because that is a very important point, it's really important to keep this in perspective. Let's talk about what an internal combustion engine is. So internal combustion engine, what is the definition? So an internal combustion engine is a heat engine that converts chemical energy contained within a fuel into mechanical energy or work, usually made available on a rotating shaft. So if you remember way back when from first year thermal fluids, we talked about heat engines, and we talked about how they were subject to Carnot efficiency. So this Carnot efficiency, this still governs the overall maximum efficiency of any heat engine, including internal combustion engines. Well, how do we release this chemical energy in the fuel? Well, it's through combustion or oxidation of fuel. So chemical energy, which are in the chemical bonds of the fuel, is converted into thermal energy. This causes temperature to rise. We know from our ideal gas law, if the temperature of a gas increases, the pressure must increase. Well, pressure pushing on an object is going to make it move. Pressure times a distance, we have a force. So this is how we get this energy or work out of the chemical energy stored in the fuel. So this high pressure exerts a large force on the movable parts in the engine. This force causes movable parts to move. We get a rotating crankshaft, or we get work out. So this is the definition of internal combustion engine. It's a heat engine where the combustion is inside the system. Now, what is not an internal combustion engine? Steam engines, Stirling engines, gas turbines. Well, these are examples of external combustion devices. So this is where combustion occurs outside the mechanical energy, or outside the mechanical system, i.e. the combustion is not occurring directly against the prime mover. If we look at it in terms of a steam engine, we see here there's a coupling between where the combustion is happening in the top chamber and between a piston that is moving in the lower chamber. Same thing what we have in a gas turbine in this other image. We have combustion occurring in this radial combustor, which is then flowing hot exhaust gas over turbine blades. But the turbine blades are not directly in the combustion zone. So the combustion is not directly coupled to the mechanical system. Now, this can also introduce potential losses, but it depends on what you're trying to achieve with the system. So these are not internal combustion engines. Okay, so as I said, this is the part of the lecture where we're now going to break down all the different components that are present in internal combustion engines. And as I said, I'm just going to pause here for a few seconds on each of these slides so that you as students can take the time to go over these in detail. I'm not going to take the time to name all these off, as I'm not really adding anything beneficial to your understanding of the internal combustion engine and the components. So we've gone through all the different components in the internal combustion engine, and the next few slides are going to look at different terminologies or different acronyms that are used when describing internal combustion engines. Okay, at this point in the lecture, we've gone through all the components in an internal combustion engine. We've also discussed some important terminology when working or discussing internal combustion engines. Please, if there is anything that wasn't clear, any of the want more information about any of the components, or you're not sure about some of the definitions, please send me an email. Please come see me during my office hours, and we should discuss this. It's very important you understand the main components, what they are, and you understand the basic terminology that was just on the previous slide. So please come see me during office hours. Please send me an email. Okay, so I'm now going to talk about engine cycles. So the most common engine cycle in terms of the automotive sector is what's called the four-stroke engine cycle. Now, as the name kind of implies, it's an engine cycle that consists of four distinct strokes, where each stroke performs a specific function that must be in a particular order for the engine to operate. So this is different than some other cycles where different processes are happening concurrently, whereas in a four-stroke, we can generally isolate the strokes into four specific functions. So the first function, if we look at this first stroke, is intake. So in the intake stroke, the piston is moving down away from the top. It's moving down, and it is sucking in fuel and air. Now, it depends if this is a diesel, compression ignition, or spark ignition. If it's a spark ignition engine, traditionally it would be taking in air and fuel at this time, although we can talk about cases where fuel might be injected later. So that's the intake. It's taking in the air and possibly fuel charge. We then have compression. Any fuel and air that is already entered into the chamber, the intake valve will close, and then the piston starts moving upwards. Well, this is going to compress the gas. So we're going to increase the pressure within the cylinder. Now, on the next slides, I'm going to talk about spark ignition versus compression ignition. So once this piston reaches the top of the compression stroke, one of two things are going to happen. The mixture is either going to be ignited by a spark, and we're going to get combustion, or the mixture is going to ignite on its own or auto-ignite due to the compression, or in other words, you're going to have compression ignition. Regardless of whether we have compression ignition or spark ignition, the next event is, or the next stroke is called the power stroke. This is where, because of the combustion event, we've already increased the pressure during the compression. Because of the combustion, we now rapidly increase the temperature, which means the pressure increases much more rapidly than simply compressing the gas. So we have a very high pressure in the cylinder, and this is going to cause a very strong force on the piston. And this is the reason it's called the power stroke is because this is where the engine actually produces useful work out. You can imagine during the intake and during the compression, the engine is spending energy on tasks that don't directly contribute to the power output of the energy, but they are necessary for the overall operation. So we have the power stroke, and now what we have left in this cylinder is a bunch of burned gas products, traditionally carbon dioxide and water. That's the main products of combustion. Well, we have to get these products out of the chamber so we can get a new intake charge and fresh fuel. So we have the exhaust stroke. The exhaust valve opens, and the piston goes up and pushes out the burned gas products. Again, this is a stroke that doesn't necessarily contribute to the power output of the engine, but it's necessary for its function. Now, if you're watching the video as opposed to looking at the slides, which I guess you are if you're listening to me, we see this GIF here, or GIF, I don't know how you're supposed to pronounce it, that looks at the 4 strokes. So if we can look here, and if I time this correctly, we have intake, compression, power, exhaust. Intake, compression, power, exhaust. Intake, compression, power, exhaust. Now, we said they are distinct strokes. Now, in reality, there is overlap between all these strokes. For an engine to function properly, you have to have overlap between these strokes. Otherwise, your engine simply wouldn't run. That's a topic we'll mostly cover again in the more advanced internal combustion engine course in 4th year. But just realize, even though we theoretically look at these as 4 distinct strokes, in an actual engine, there has to be overlap between these strokes in order for the engine to function. So once again, this is a very important concept. If anything is not clear on this slide, please email, come see me during office hours. Okay, so we said we were going to look at 2 types of 4-stroke engines, and we mentioned the word spark ignition and compression ignition. So as we said, the main difference, or really there's only 2 main differences in spark ignition versus compression ignition. In spark ignition, the fuel-air mixture is ignited by an external spark. And now generally, the traditional SI engine is used in cases where the fuel is gasoline. And generally, or I should say before maybe 2010, all gasoline vehicles used what's called a pre-mixed charge, i.e. the air and fuel were already mixed as they come in through the intake. Now, as you learn in your internal combustion engine course, and I'm just going to mention here, more modern gasoline engines use what's called direct injection. So they take in an intake charge of air without any fuel, and then they inject the fuel right before the spark. So that's what's called gasoline direct injection. Now, that does change things a bit, but for this course, we're not going to look at that complication. We're just going to consider spark ignition engines where fuel and air are taken in as a pre-mixed or already mixed charge. So in order to analyze this from a thermodynamic standpoint, remember when we had the Carnot engine, we were able to analyze it from a thermodynamic standpoint and come up with the Carnot efficiency. Well, we can look at these 4-stroke spark ignition engines, and we can do a similar type of analysis. Now we're going to look at the bottom here, the Otto cycle. And it's looking at the Otto cycle on a pressure volume diagram. Now this is an Otto cycle is an idealized theoretical cycle. Just like the Carnot cycle, there is actually no Otto cycle engine. There is no real Carnot engine. It's just this is the most idealized spark ignition engine we can hope to achieve. Now in this idealized engine, we kind of have 4 different phases as we expect. So if we start at point 0 on the Otto cycle graph, we can go over to the exhaust, or we start with the intake stroke, and that brings us to point 1. From point 1, we have an adiabatic compression, which brings us to point 2, and then we have heat addition at constant volume. Now, the reason we have heat addition at constant volume is for spark ignition, we assume the combustion is extremely, extremely fast. So as soon as the spark happens, almost everything burns. This is an idealization. This isn't actually true, but it works out. It's fairly accurate for spark ignition engines. We then have a power stroke or adiabatic expansion, and we then have loss of heat. Now this heat ejection is actually not what really happens. What really happens is heat is lost from the system due to the exhaust stroke, where we're exhausting the gases out. Now there is some heat transfer from the hot gas to the surroundings, but this isn't quite an accurate reflection of what happens. And then we have the exhaust stroke and we're back at zero. Now, when we compare this with a real cycle, what actually happens in a spark ignition, we see basically all our really smooth curve and straight up and down lines. Well, they're kind of curvy. When we look at the intake and exhaust, they don't exactly follow a constant volume process, so there is some losses in energy during these intake and exhaust. We see the compression stroke. It has a bit of a curve going up to state 2. The path from 2 to 3 is not quite constant volume. The path from 3 to 4 is nowhere near what you would expect if it was an adiabatic expansion. The curve does not follow what you would expect for adiabatic expansion. And again, the heat loss is not exactly straight up and down constant volume either. Now, when you look at it though, overall though, the Otto cycle is a fairly good representation of the real engine cycle. Okay, so that was spark ignition engines. What about compression ignition engines? Well, as I said, the main difference for compression ignition is instead of the combustion starting when you have a spark, the combustion starts when you inject fuel. So what implication does that have? Well, essentially, you're compressing the air to such a high level, so very strong compression, that as soon as you inject any fuel, it starts burning because the pressure and temperature has already been raised to such a high degree because of the high compression ratio. In compression ignition engines, we also use fuels that are easy to auto-ignite. They have a high propensity to auto-ignite. Diesel fuel is easier to ignite than gas. That's why diesel is generally used in compression ignition engines and gasoline used in spark ignition. So the main difference between spark ignition and compression ignition: spark ignition combustion starts because of a spark. Compression ignition starts because of high temperature and pressure from compression. And how do you control when the combustion starts? In the spark ignition, it's whenever you have your spark, what your spark timing is. In a compression ignition engine, it's whenever you inject the fuel. That's how you control the combustion event. Okay, so how does this compression ignition engine look in terms of a PV diagram? Now, the previous idealized cycle was called the Otto cycle. I guess whoever created this idealized cycle wasn't very creative, and instead of calling it like the ideal CI cycle, they called it the diesel cycle. Now, as I said, most compression ignition engines do use diesel. There are other variations of engines that are compression ignition that use gasoline, HCCI, and other variants as well. So even though this is the diesel cycle, it's not only for diesel fuel. I think that's kind of a bit of a misnomer. Okay, so what's the main difference between the diesel cycle and the Otto cycle? Well, the main difference is the assumption of what happens during the power or during the combustion. The combustion in a diesel engine is assumed to happen at constant pressure, i.e. the combustion happens over a much longer time frame in terms of the piston movement. In other words, in a diesel engine or compression ignition, combustion is happening during a good majority of the power stroke. It's not like as soon as you inject the fuel, it all burns very rapidly like it does in the spark ignition. So we still have our intake stroke, we still have our adiabatic compression stroke, but in the fuel, the heat from combustion is assumed to happen at constant pressure. So basically we have a difference between constant volume heat addition versus constant pressure heat addition. We then still have the rest of our power stroke and adiabatic expansion, and then we have our heat loss and exhaust stroke. And this is the idealized cycle, and there's a number of different parameters, more so than the Otto cycle. We have the compression ratio is the same, but then we have these pressure ratios for state 2 and state 3. So there's more parameters to define a diesel cycle than there is for an Otto cycle. How does this look in a real compression ignition engine? Well, similar to the Otto cycle, it follows mostly the same path, except the lines aren't as perfect at the junctions as you would expect. So at the same thing, the exhaust and intake stroke aren't exactly constant pressure. The transfer from point 2 to point 3 is kind of a bit more curvy rather than a sharp point. What we do actually notice is the diesel engine cycle actually does tend to follow the real cycle from a diesel engine tends to follow the ideal cycle a bit more closely than for a spark ignition engine. And this has implications for efficiency. So the last thing I want to talk about in this lecture very briefly is the two-stroke engine. Why is it very briefly? Well, because two-stroke engines are not typically used in automotive applications. The main reason is because two-stroke engines have emissions that are much higher than four-stroke. So for a given power level, two-stroke engines have much higher emissions than four-stroke engines. And that's why they're really not seen in modern automotive applications, because they simply would be too difficult to design a two-stroke engine that meets the emission requirements for a vehicle. Now, the advantage of a two-stroke, though, is it's mechanically simpler, and for a given amount of fuel, you can actually get more power out of it. So in a way, you can think of them as more efficient in terms of getting power out for a given fuel input. However, that comes at the penalty of more emissions. Now, what is meant? So how do you go from four strokes to two strokes? Well, you have to combine different functions on different strokes. So if you look at what this engine does, you can see that while it's going through its power stroke, so we have, say, compression, and then we have the power stroke. What happens is at the bottom of the power stroke, we actually have intake and exhaust happening at the exact same time. So we're at the bottom of the power stroke. What happens is some ports open, the exhaust port, a set of valves, and the intake port. We see first the exhaust port opens. Once we're a part of the way down the power stroke, the exhaust port is revealed or exposed by the piston moving past it, and we get exhaust. The piston moves a bit further down in the power stroke, and then the intake port is let open, and that goes into the cylinder. Now, I also notice it's taking air from the crankcase. In a two-stroke engine, the crank itself actually acts as a mini compressor to pre-compress the air fuel mixture before it reaches the cylinder combustion chamber. So basically, you can think about the way that a two-stroke engine works is it combines the power, intake, exhaust stroke into one stroke. And the only stroke that is more isolated is the compression stroke. As you can see, once the compression stroke starts, generally the intake and exhaust processes are already stopped. Now, as you can imagine, during the compression stroke in a two-stroke, some of your intake fuel and air is going out the exhaust port before anything gets burned. That is why two-stroke engines have much higher emissions. You can see some, and particularly unburned hydrocarbons. The fuel goes straight through the combustion chamber without ever being burned. So two-strokes are great for small applications because you can make very small engines still produce a high level of power. So two-strokes are very common on motorcycles, a lot of your yard equipment, chainsaws, hedge trimmers, and stuff like that. If they're high performance and they're a steel, STIHL, like they should be, they're all two-strokes because you can make a much smaller engine for the amount of power output. Again, emissions are somewhat of a problem. And to just kind of relay how much of a problem emissions are with two strokes is the amount of emission you would get from a two-stroke small engine that would run, say, a chainsaw. Now, you know that people can have an idea of the size of a chainsaw. Running the chainsaw gives as much emissions as running a big engine that would be able to move a car. So these engines are very bad in terms of emissions. Okay, so that's everything I wanted to talk about in this lecture. I'm also going to introduce another thing that I want to do during this course, and that's called the ticket out the door. Now, normally if this was in a face-to-face lecture, at the end of each lecture, I give everybody a small slip of paper, and they would write on it something you learned and something that where the explanation was not clear or it was confusing. And this really has two purposes. One is it makes you internalize one main concept that you learned today. It's easier to remember if you reflect on what you just learned. The second point is more so for me. It does help you kind of think about, okay, what do I still need to learn, or what do I need to ask the professor later? However, it also helps me in trying to improve my lectures and try to make things as clear and straightforward as possible. So what we're going to do is we're going to do tickets out the door, but we're going to do them over Blackboard. So just like with the Think, Pair, Share in the first lecture, I'm going to set up another discussion board where you can state something you learned and something where the explanation was not clear or confusing. And I will check this discussion board and make posts on announcements on Blackboard to try to address things that were not clear or confusing. All right, thank you very much, everyone, for watching this lecture, and we will see you next time. All right, take care.